So we're going to talk about some kind of odds and ends for regression. So we saw ordinary least squares regression 1 in n dimensions, then we saw nonlinear least squares in multiple dimensions, and then I mentioned, but we didn't cover, and we won't cover multidimensional y. So I actually have something called lecture review inside the course notes, and the lecture review is kind of like where you find all the different cases you might have. So we'll cover 3 and 4 in just a moment, but I just want to make you aware of this. So if you have, ordinary least squares in one dimension with one dimension in y, one dimension in x, then you look in lecture 1, n dimensions in x, one dimension in y, lecture 1, n dimensions in x, but it's nonlinear, then lecture 2. I should add to this, and then if you have nonlinear with n and n y dimensions, then that's in lecture 2 as well. And then we saw how to linearize in lecture 1. And then we're going to look in lecture 3, and this shows us how to take categorical data. So categorical data is something like a yes or no kind of data. Or categorical data can be something like, maybe somebody is, I don't know, maybe someone can be 5 different professions, and you can represent those 5 professions as categories. Or maybe the categorical data could be the suit of a card. A card can be a spade or a heart or a diamond or a club. And then in lecture 4, we have a different kind of uh, regression that's called the weighted least squares regression. And that's if you have measurement error in x or y or both. So that's what we'll cover in lecture 4. So in lecture 4, you can have measurement error in x and y. So something like maybe your x is like the weight measured on a balance, and your balance has some known uncertainty. Or maybe you've calibrated your balance using confidence intervals, and then you want to use that information in your regression. And then in lecture, we won't cover this in the lecture review, but if you ever, if you want to, you can study this. There's some examples of different kinds of problems. So there's just different kind of problems in these examples, and it tells you what kind of regression technique to use. For example, we'll just look at this one here, example 2. We have data on selectivity in a membrane as a function of temperature. And if we added graphene nanofibers to the membrane. So we have a membrane, and selectivity is a number that represents how much of one chemical species goes through a membrane relative to another. So for example, if we have a membrane and maybe we're trying to separate out carbon dioxide, so that's a common thing for climate change. You want to separate carbon dioxide from the air so you can sequester carbon dioxide to reduce carbon emissions. You might have a membrane that can separate carbon dioxide from O2 and N2, the other main components in air. And then we want to see which temperature to operate at, because as you change temperature, maybe the selectivity changes. And then, everyone likes to do this in science, is they like to put graphene or nanofibers inside of crap to make it better. It helps your publication impact factor. So maybe they put graphene nanofibers in there. And then you can see, does that help the membrane? So this is an example of a categorical variable, right? It's a yes or no question. So in this example, how do you fit a model to this data? And this is descriptions of selectivity. So basically, this is one where you have ordinary least squares, but you have categorical data. All right, and then this is an explanation of it. So this one here, we have categorical data and the graphene nanofibers, and then we have temperature as a continuous variable. And if we assume it's linear, we can use ordinary least squares. Maybe you want to fit some nonlinear equation, but if you think you have a nonlinear equation, you have to, be able to write it down. Okay, so go to the lecture review in the lecture notes to find an overview of all the different things covered. And it also describes how to choose which regression technique to use. So let's take a look at categorical data. So categorical data is basically whenever you have a discrete number or some kind of discrete uh, uh, effect on your data. So maybe we have a potential drug molecule that can improve your test taking abilities. This sounds great as some kind of drug we can take to do well on our final exam. So you might set up your experiment to give 10 people the drug and 7 people are given the placebo. Why 10 and 7? One of the most common things that happens in drug trials is that people drop out of drug trials. So maybe you had 10 and 10, but 3 people dropped out. So here are the results on the exam. So we have people who took the drug and then these are their final exam scores. Then we have people who did not take the drug and these are their final exam scores. So we want to answer, did the drug make a difference? Now, this is a great example of a hypothesis test, right? You could immediately use a hypothesis test for this. So this is an example of the sum of ranks hypothesis test, right? So Wilcoxon sum of ranks, because we have unpaired data. This is not the same person taking the exam. These are 2 different groups of people taking the exam. So we can compare, are they the same? So we get a p-value of 0.04 if we do that comparison. So that means that we can reject the null hypothesis and we can say there is an effect of taking the drug. So there is an effect of taking the drug on your exam score. But let's say we want to know how strong is the effect, like how many points would I expect to improve my grade by taking the drug? Maybe the drug has side effects and you want to know, if I improve my grade by 5%, is it worth having permanent liver damage? I don't, we want to know how much does it improve. So we're going to use what's called a categorical variable or a dummy variable. And that means that we're going to have an x value. Do I have the equation for it? That's kind of hard. Yeah, here's what I want to show you guys. We're going to represent the equation for your exam score as being a constant beta naught plus beta 1 times this indicator. And this indicator or categorical variable, this is a 1 when we took the drug and a 0 if we didn't take the drug. So if we plot our data here, we basically show this is my indicator variable, my drug variable. So it's 0 when we didn't take the drug and it's 1 when we took the drug. And we're going to fit a line to this. So if you look at the data, right, you might not think, hey, can we do linear regression on this? But once you turn your drug indicator to a 0 and a 1, you can actually just do a best fit line. It looks unusual, right? Like we don't have a bunch of data in the middle here. We have data only on the ends of the line. But you can still do a linear regression here to assess how well the data fits. And it's actually just completely straightforward. It's just ordinary least squares regression. And we fit a line to it. It's very straightforward. Okay. And then note what you're going to find is that the intercept, maybe you don't care about the intercept. The intercept is like, what do people on average get in the test? You might care about the slope. That is, how much does it improve to take the drug? And the slope is 7. So it tells us that taking the drug improves your exam score by 7 points on average. Now, what's nice about doing a regression for this is that you can get hypothesis tests and confidence intervals. So we can say you will improve on the test, 7 plus or minus 5 with 95% confidence or something like that. But one of the cool things you can do, so the confidence intervals are nice because you can give uncertainty, is you can, instead of doing the Wilcoxon sum of ranks, you can see, is the slope non-zero? So you can do a hypothesis test on if the slope is non-zero. And that is the same thing as testing if there is an effect on the drug. So doing a hypothesis test here is the same thing as doing the hypothesis test with the raw data with the Wilcoxon sum of ranks. So I'm not going to go into this because we saw this in our last lecture. We get a p-value 0.032. Now you may be wondering, why is it more significant? We saw that the Wilcoxon sum of ranks gave us a p-value of 0.04, but here we get a p-value of 0.03. And this comes back to this discussion we had about non-parametric methods. So the Wilcoxon sum of ranks test is a non-parametric hypothesis test. The non-parametric hypothesis tests are powerful because they don't make any assumptions about the data, but it has it's harder to show an effect. Like it's harder to reject the null hypothesis. Here, we have not only assumed that the data is normally distributed noise, we've also assumed that it's described by this equation. So this is an even stronger assumption than before. So we're assuming we have normally distributed noise, and we're assuming that the model for the test taking is beta naught plus beta 1 times this indicator variable. So with this stronger assumption, it's easier to reject the null hypothesis, and so we get lower p-values. Okay, so we made a stronger assumption about how the data behaves, and because of that, it's easier to reject the null hypothesis, so we have lower p-values. Now, which is correct? Well, it's kind of like, you know, up to you to decide. You can make more assumptions, like you can assume that the data is going to be described by a line with normal noise. That's a stronger assumption, but it's a reasonable assumption. So then you get lower p-values. Or if you don't want to make that assumption, you can, say, I don't want to assume that it's normal and I don't want to assume it's linear, then you can use the Wilcoxon sum of ranks test. So either way is appropriate. What's nice about assuming this model equation, though, is you get more to it, right? You can have confidence intervals, you can have the strength of the effect, and p-values. Okay, so what is the point? The point is, if you have categorical data, you can do all of the same regression stuff by using indicators, which are 1, in the drug category and 0 in the other category. So this is a binary variable, right? This is an on or off variable. We'll see in a moment how to deal with more sophisticated examples, but for anything where it's like on or off, you can just use a 1 or a 0 and use all of the same tools we developed for linear regression. Okay, so are there any questions on this? Okay. Now let's say that I have, so let's say I have multiple categories. Okay, so I don't, just a moment here, I want to skip ahead here to make sure that we cover this. Okay, yeah. All right, so let's say I have multiple categories. So I am doing plant growth. So I can either fertilize the plant or not fertilize the plant. And I can put the plant in direct sunlight or not put the plant in direct sunlight. So you can think about this as that I have basically, I can have fertilized and indirect sunlight, unfertilized and indirect sunlight and fertilized, etc. So there's basically all these different categories. So I can represent that as a series of indicator variables, right? So I can have this for sunlight and this for fertilizer. Excuse me. But we have to go farther than that. There's something else that could happen, is that it might be that you need to have both occurring simultaneously. That is, the effect of fertilizer and sunlight only matters when you have both happening. So we can indicate that by having a product of these two. So notice if you multiply this indicator for sunlight and indicator for fertilizer, it will only be 1 if they're both 1. Okay? And this kind of makes sense, right? If you think about plant growth, whether or not you put fertilizer actually doesn't matter if the plant's not in the sun, right? If you have a plant and it's not getting sunlight, whether or not it has fertilizer doesn't matter. It can't grow without sunlight. Then on the other hand, if you give it fertilizer or not, and it is in sunlight, well, that's another thing. So there is some kind of interaction. Okay. So if we think about the full equation here, we're going to have this expression. So G is going to be maybe the mass of the plant or the height of the plant. We have an intercept, just some beta naught. And what does beta naught represent? Beta naught represents how much does the plant grow if we give it no sunlight and no fertilizer. So we might expect beta naught to be 0, in fact. Okay. Then we have a term that is just for giving it sunlight. And we would expect this to matter. Then we have a term for just giving it fertilizer, regardless of if it has sunlight or not. We might expect this to be 0, right? This is how much it grows just by giving it fertilizer, regardless of whether there's sunlight. And then there's the interaction. The interaction is if we have sunlight and fertilizer, and we expect this term to matter, right? Because really the fertilizer only kicks in if you're giving it both sunlight and fertilizer. And then we have, of course, our noise. So the key for this example is this interaction term. Here is some data. Okay, I'm not going to go too much in depth here, but I put the data into an X matrix, right? These are all multi-dimensional regressions, so I have to build this X matrix. This is my fertilizer, this is my sunlight, and then here's the actual amount of growth here. So here's my X matrix here. So this is my X data, this is my Y data, and then here I separate it out. So I have to do a little bit of work here, right? So the dimensions my X matrix for the n-dimensional regression, I need to have a column of ones for my beta 0. Then I need to have my indicator for the sunlight, my indicator for fertilizer, then my product. So here's that data. And so it's a 4-dimensional regression, right? Okay, so it's very straightforward to do this regression. Just plug it all in here. And so interestingly, my beta 0 is not 0. Surprised about that, but I do see that the fertilizer doesn't really matter, so this is my beta 2. And then here's the interaction. Basically, fertilizer and sunlight has a very strong effect. This is my beta 4, so the interaction has a big effect. Sunlight has an effect. It looks like giving it fertilizer if you don't have sunlight actually is bad for the plant. I don't know. Maybe it makes sense. And then, of course, we can do uncertainty analysis. We can get confidence intervals for all of these things. So you can see that this term here, it's 0.42 plus or minus 0.92. That means it's approximately 0, right? It almost doesn't matter whether you give it fertilizer in the absence of sunlight. But then once you have sunlight, definitely a very strong effect. And you could give a p-value for that. You could go and do a hypothesis test to say, does fertilizer matter without sunlight? And you would find the p-value is definitely not less than 0.05. Okay, so that's how we do categorical variables if we have multiple categories, right? So this is, we had multiple categories. The plant could be fertilized or unfertilized, in sunlight or without sunlight. And notice that if you do have these multiple categories, you have to have this interaction. Okay, you can't just make each category an indicator variable. You have to have this interaction effect in our equation. We have to have this extra term if there's some combination effect where both categories have to be true to see something. And this applies to all kinds of things, like let's say we're looking at not plant growth, but maybe muscle growth, right? And we're doing muscle growth, and maybe it's like, you have to eat and you have to sleep. And then maybe there's some interaction that only your muscles grow if you eat and sleep enough, right? So you could imagine some kind of multiplicative effect there. It could be something like, some chemical reaction. You need to have both, catalyst and stirring for it to happen. So this interaction thing is really important. You want to make sure you have that in your equation. Okay, so are there any questions so far on categorical regression? So we're going to cover this a little bit later, but this kind of idea of like having these different beta knots and then doing hypothesis tests to see if they matter. This is part of something called a design and analysis of experiments with statistics. Like, notice that in the previous example, I was able to prove that fertilizing only matters if the plants have sunlight. And so you could have designed an experiment to show whether or not fertilizing matters with sunlight. Or you could design the experiment of whether or not your drug matters for taking your test. And we didn't talk about this, but like the XY values that I chose, like I chose, 10 people in the control group and 7 people or 10 people in the drug group, 7 people in the control group. If you're designing a drug trial, you might want to know how many people do I need to enroll to show an effect, right? So we haven't talked about this, but you could also choose which experiments to do, and choose those with an analysis in mind. Like, how many people do I need to have to show an effect, or what's the minimum number of people I need to have to show an effect? Like, I don't want to have 1,000 people take my drug. I want to use as few people as possible. So this kind of gets into design of experiments, and we'll cover that next week a little bit, but it's a huge field, so we're not going to be able to cover all of it. I just want to make a note here. There's some information in the Langley statistics book about this. And one more thing here is if you have a category which has more than one possible value, so like let's say you have color, so let's say you have like red, blue, orange. Now it's not correct to just have like a 0, 1, 2 for these things, right? So you might think, hey, if I have red and blue, I could have a 0 and a 1. Maybe for red, blue, orange, I have 0, 1, 2. You can't do it that way. That would imply that like, red plus blue equals orange. like if you have a 0, 1, 2. Or it might imply that blue is twice as, or orange is twice blue, right? So it has all this meaningless consequences. So what you need to make sure you do is you need to have indicator variables for each of them, okay? So like, let's say we have, something could be red or blue or orange. You need to have indicators for red and blue and orange. Now notice you don't need an interaction. Right? We don't need a red times a blue because you can only be either red or blue. You can't be red and blue at the same time. So there is no need for interactions, but you do need to have indicators for each one. So you have to have an indicator for red, an indicator for blue, and an indicator for orange. But no product. You don't need red times blue because you can't be both red and blue at the same time. So this is just a small note, is that if you have categories where you can have multiple values, um, it's incorrect to like use one variable for it. If you have a category which can have multiple values, or you have categorical data with more than one category, you need to split up it into a bunch of different binary values. Okay, so if you have like 10 categories, then you're going to have 10 indicator variables. Okay, are there any questions on categorical regression? All right, so we're a little bit short on time, so I'm going to just give a quick overview of lecture 4, and I'll leave it for you to look at on your own. Let me just turn on the lecture. So lecture 4 is quite short, but there's two things to take away. The first thing that we cover in lecture 4 is how to plot with error bars. Okay, and it's very straightforward. Instead of using plt.plot xy, we use plt.errorbar, and then you can pass in what is the error in your y. So you can have y error or x error. This is just me plotting with O's. And then this cap thick, it's up to you, but it's just about the format of them. So notice here on this XY plot, I have little bars indicating the Y value uncertainty. So that's point 1 of this lecture. So you can take a look, we have, if you have Y and X error, if you want to have multiple values, so you can pass in a list here. So instead of just constant Y uncertainty, maybe you have different uncertainty at each value. So notice we have different uncertainty here and different uncertainty here. So you can have a list or multiple values. Okay. Now, where do these numbers come from? These uncertainty numbers come from basically you might have these x's coming from an instrument with a known uncertainty. And we'll talk a little bit about error propagation later, but it could be from all kinds of different sources of uncertainty. Maybe these x values came from a regression themselves, or they came from data gathered, and so these are confidence intervals. So these are just how to plot the error. Okay. Now in this lecture, basically we cover 4 different cases. You have uncertainty in y, uncertainty in x, uncertainty in x and y, and you have multiple y values. So like I said, we don't have time to go through this lecture, but essentially if you're doing a regression and you have uncertainty in x or y, or x and y, you can just go and look at the modification. So in general, we don't actually change anything. The only thing that changes is your standard error equations. So for uncertainty in, this is uncertainty in, I already forgot. Uncertainty in y, the only thing that changes is your equation for the standard error. That's the only thing that changes. So these are just the equations for the standard error. The only thing that changes is just this little plus uh, uh, sigma eta squared. So this is the uncertainty in y. You just have a additive term here. Everything else is the same. These are the same equations for ordinary least squares. And for case 2, this is an example of it. Then for case 2, everything is the same except for we have a little extra term here that accounts for the uncertainty in x. So everything's the same. It's only the error analysis that changes. There is one thing I'll mention for case 2, is there's something called attenuation error. And I don't want to, we're not going to go, I just don't have time. I won't go too in depth in this. But essentially, if you have uncertainty in X, it becomes harder to do the regression. So uncertainty in Y, nothing changes. Uncertainty in Y is totally fine. Everything is normal. But if you start having uncertainty in X, your independent variable, um, it becomes harder and harder to spot a correlation. Now, this doesn't matter, like we don't really do anything, but just so you know the word, if someone says attenuation error, or attenuation error, it means if you have a lot of uncertainty in X, it gets harder and harder to do regression, as in it's harder and harder to estimate the alpha and beta. Their magnitude gets smaller. Now, you can't account for this. You can't fix this or do anything about it. But if you have very high uncertainty X values, it's harder to calculate slope. Okay? Intercept doesn't matter as much, but slope changes a lot. All right. And then I'll just mention again, things change here. If you have X and Y uncertainty, there's an extra term here. And the last thing I want to mention, this is a very simple thing, is that if you have multiple Y values, like you did a repeated measurement, like you have multiple measurements here, to do the regression, you just include all of the data. Like if you have, one measurement here, and 10 measurements here, you just treat it as if you have 12 pieces of data. So this is the, just you have 12 pieces of data, so it doesn't change anything. This is obvious, but it comes up a lot. I get questions a lot from people is, hey, if I repeated a measurement multiple times, how do I do the regression? You just include all of your data. Okay, so we're just about out of time. And I just, nothing significant in this regression, this lecture. Basically, just the equations change a little bit. And in some of these examples, like I say, here's an example where I have a constant uncertainty uh, of 2 kcals per mole in my X value. How does it change, right? So this lecture is pretty straightforward. You just have a small change in all of your equations. Okay, I know I blew through this quickly, but are there any questions on this lecture? So the 2 points are how to plot with error bars, and then just there's small changes to your equations. There's just small changes to your standard error equations depending on if you have uncertainty in X or Y or both. So any questions on that? Okay, if there are no questions, that's it for Unit 12. Like I said, there's this nice review where it has all the different regression cases we covered. And I guess then I will see you all tomorrow at recitation.